This is Brian Putt. Today I'd like to talk about the relationship between the exponential and the Poisson distributions using Excel. I'm also going to be using SIPmath, which is a free tool that's available for probability management. Why are these distributions important? Well, they're used in queuing models. And there's two types of queuing models. One's a discrete event simulator, which uses the exponential typically for arrivals and service times. And the other is the time slice simulator, which generally uses the Poisson for both the arrivals and the service time. So I don't want to go into queuing models too much. I really just want to compare the two distributions. So let's flip over to a model and see how we can compare those two distributions. Here I have a model where I've got this kind of the organization I'd like to use to demonstrate. And we've already initialized this for SIPmath, so we have a PM table and a PM math chart data. So the first thing, let's talk about Poisson. Poisson is a discrete distribution, so it's going to give you integer numbers. Let's assume for discussion purposes, we're going to look at a 5-day time period. And in this time period, we are expecting 5 arrivals. That's the average. So let's generate that Poisson distribution. So I want my result to be here, and I go up to SIPmath Modeler Tools, and I'll generate input, and I'll generate a Poisson. And I want it to have a lambda or mean of 5. And I need a random cell, which I'm going to put right here. I say OK. I now have my random variable. Let's look at that distribution. So SIPmath define outputs. We'll call this the Poisson. And then let's graph it so we know what it looks like. And we can see that this distribution is in fact a stair step with values of, it looks like I have a value of 0, 1, 2, all the way up to, looks like 13 in this particular case. All right, now we want to talk about exponentials. So in a 5-day period, if I expect to have 5 arrivals on average in my Poisson, what is the time between arrivals for the exponential? Well, it's 1 day. So really, the exponential is equal to 5 days equals 5 days divided by the mean arrivals from the Poisson, which gives me 1. So one arrival per day. That's what I would expect. Now let's generate that random variable. SIPmath generate input, exponential, and it's going to have a mean of 1. And we'll give that we'll define that as an output as well, so we can look at that. Define that as the exponential. And we'll graph that so we get to see what that looks like. Remember, you do not have to graph every variable that's generated. And so that's our exponential. It has an average of 1. The Poisson has an average of 5. Well, these don't look at all alike. Well, what we really want to ask is, if I had a bunch of exponential arrivals, and I could count how many arrived in that 5-day period, then it should be equal to the Poisson. That's my hypothesis here. So let's generate a bunch of these exponential arrivals. So let's define, starting with 1 here and going down to 25, I think it is, what I had. Let's put in some mean arrival times. So what I'm going to do is I'm going to highlight these 25. Come up here to go to SIPmath, generate input, exponentials, and they are all going to have this this distribution of 1, right? So we'll say OK. So now I've got my mean arrival times. So if I start at 0, the arrival time for the first person is equal to the arrival time of the last one plus the interval arrival times. And I can copy that down. So how many arrive in the first 5 days using the exponential? Well, we can just, in this particular trial, we can just count them up. And so we can see that there are 2. Now, how can I get that automatically? Well, one way to do that is to say equals match. And I want to match 5, the value 5, because that's how many days I have in this list. And it gave me 2, which is what I expected. Let's just check this a little bit. We'll come over here to get trial information. And let's look at trial, that's trial 7. Let's go look at trial 8. Trial 8 also had 2. Well, that doesn't help me. How about trial 9? Trial 9 has 6. So I have 1, 2, 3, 4, 5, 6. So that all works. So let's close. And so now we want to define this. Actually, I think as a result, I want to put this over here. So we'll just move it over here. Okay. So now we'll define this as an output. SIPmath define outputs. And we'll define that as the how about arrivals with exponential. Okay. And it gives me that because I had some blanks in there. I say yes. Now, okay, this is a really good point here. SIPmath, kind of because I'm simulating after each change, if I've got an error of some sort, it's going to tell me something's wrong. I need to figure out what's wrong. Now, in this particular case, remember I mentioned there was a possibility of 0. So what I need to do here is if the answer is 0, let's say if this first time was more than 5, so that no one arrived in the first 5 days, the match command is going to have an error. So what I could say here is if this is greater than 5, we'll put a 0. Okay, that means no one arrived. Otherwise, we'll do this match command. And let's see if that helps us get the right answer. And now we'll define it as an output. And we'll call this, well, we decided to call it exponential arrivals. How about that? Okay, so now we've got our distribution here. And we're going to graph that. And there we have our graph. Now what I really want to do is I want to compare these two distributions. So I want to combine these two distributions. I can do that by taking this graphic and copying it, Control C, coming up here and picking this one and saying Control V. And now I have them together, and I'll add a legend. And there is the comparison, and you can see that they are the same. So now the question is, well, Brian, you did that for 5. What if it was something else? What if I made this mean 8? There's 8. What if I did 3? So what if I wanted to say this was equal to 0.5? And then figure out how many Poissons I have. And that's going to be equal to 5 divided by this 0.5. So if they arrived every half day in a 5-day period, there would be 10 arrivals. And as you can see, they match again. So I hope this helps you in understanding the relationship between the exponential and Poisson, and why what I can do either type of queuing model, and they're really going to be the same sort of thing. I may be able to get different statistics. If you want to learn more about SIPmath, you can visit www.probabilitymanagement.org, where you can download the SIPmath 3.0 toolbar. You can also view my instructional videos that are available on YouTube, my YouTube channel. And you can contact me at brian@theputz.com or on LinkedIn. Thank you for watching.